Okay, so my name is Eric Siegel, and welcome to the presentation about the RBRlegato CTD for ocean gliders. You probably know that RBR does many things. Of course, we make sensors to measure the ocean. We combine the sensors together to make loggers and CTDs. We integrate those, and we work with partners to create larger systems. This is an example of the Del Mar Oceanographic Wire Walker. But we also make some OEM products. So these are products that RBR makes, primarily CTDs, and other people integrate them into their system. So you may not always know they're RBR CTDs that you're using in the integrated systems. And primarily the OEM products that we make are CTDs for Argo floats and CTDs for gliders. And that's what we'll be speaking about today. So the OEM folks choose RBR for 4 primary reasons. One is that we have very low power electronics. The second is that we have very high accuracy sensors, all calibrated to WOS standards. And then the third and fourth reasons are because we're quite modular. So we can provide what we call the sensor hub, which allows the RBR CTD to actually log and control other types of sensors. And we make really nice customized integrated solutions. So everything we make for the gliders and for the Argo floats are customized for their particular needs. In terms of accuracy, the RBR CTD is calibrated to WOS qualifications. So this means that our conductivity has an accuracy of 0.003 millisiemens per centimeter, which is the same as the pump CTD you might be used to on some of your gliders. Temperature accuracy is the same as that as well, 0.002 degrees Celsius. We actually have very high accuracy for depth, 0.05% of full scale. And our power is very low. So the RBR CTD only uses about 18 millijoules per sample, where the pump CTD is published at 175 millijoules per sample. So what this means is that we provide really high quality measurements, maybe even more accurate in depth, but the savings in power is really dramatic. On an Argo float, when you calculate all the other things running power, such as the rest of the system, the telemetry, and the ballasting system, our reduction in power actually pretty much doubles the length of an Argo deployment. So that means that it brings the cost per profile down by about a factor of 2. And as you can imagine, the lower power can have some real benefits for ocean gliders as well. So the RBR CTDs have been integrated into almost all of the Argo floats, and they've been deployed all over the world. And what the float folks really appreciate about the RBR CTD is, as we talked about, the low power, but also that there's no pump needed. So the RBR CTD is naturally flushing, which means there's no pump. And that gives a couple extra values. One is that you can sample all the way to the surface. You don't have to turn the pump off as you get closer to the surface because of pulling in surfactants and contaminating the sample. We can measure salinity all the way to the surface. The other is that because there's no pump, there's no noise. So the measurement is totally silent, which can improve measurements when, acoustic measurements, when you're trying to listen for marine mammals or rain or wind or other things underwater. And finally, we have very high sensor stability and can function, as I mentioned, as a sensor hub. We can pull in other sensors, we can integrate them together, we can feed it out as one data set. And as you know, gliders are very similar to Argo floats in many ways. So a lot of the value that the Argo program has derived, the glider community is starting to derive now. And that's with the RBRlegato CTD. So the Legato CTD is not a new CTD per se. It's really an evolution of RBR's CTD technology. So many of you are familiar with the standard RBR CTDs that look like pretty much a classic CTD. The Argo CTD is the same conductivity cell, temperature, and pressure sensor. And now all of these have been pushed over into the Legato CTD. It looks different from what most people expect a CTD to look like, but it's really the same components. There's still the conductivity cell, the temperature cell, the pressure sensor, and all of the electronics inside. Let me just mute everyone except for myself. Okay. The word legato is a musical reference for smooth, connected, and carefully integrated. And that's what we wanted to provide for the glider community. So the legato comes in 2 flavors. We have what we call the wet bay and the dry bay. And as I mentioned, it's still all the same components. There's the inductive conductivity cell here, there's a thermistor here, and there's a pressure sensor, and all the electronics are inside. The wet bay is suitable for installation on gliders where it's surrounded by water, and it's a fully watertight system with one MCBH connector out the back. The dry bay is for gliders that have a dry section inside, where the electronics aren't protected by our housing, but are held within the glider itself. And we have an O-ring groove and a bolt pattern. So the general specifications for the Legato are such that it's designed to fit in the standard GP CTD bay. This is nominally 2-inch by 7-inch bay, and it's a direct drop-in replacement. That means that the O-ring fits the same system. It means that the bolt patterns fit, and it really can be a drop-in replacement for the GP CTD. It's rated to 1,000 meters. The standard system samples at 2 Hertz and has a 1 second temperature time constant, but we can also make it in a fast mode. And the fast mode, it has a 16 Hertz sample rate and a much faster response thermistor at 100 milliseconds. The entire system is naturally flushing, which means no pumps required. And as I mentioned, it has 18 millijoules of power sampling at 1 Hertz, which is about a factor of 10 lower than the GP CTD. Same accuracy as the other CTDs that you're used to, and a custom design to fit each glider. I'll show you some pictures as we move forward about how these have been integrated into many of the gliders, and you'll see that we've made some customizations of each Legato to fit those gliders. So what this is offering the researchers are a lot of new opportunities. First, with much lower power, it means you can extend your glider missions, or it means you can just sample more. Instead of maybe just sampling on the descent or ascent to save power, you can sample in both directions. Maybe you can even sample at a faster sample rate. We also improve measurements through gradients, and we're going to talk about this towards the end of the presentation. The fact that the thermistor is so close to the conductivity cell helps, and we provide some post-processing tools in RSK tools, which is a free MATLAB toolbox to help you align the conductivity with the temperature to reduce salinity spiking. Thirdly, we have this user removable wet bay solution. This is removable with a wet pluggable connector. There aren't O-ring seals that you have to deal with, and you can pull it out of your glider, send this block here to RBR, and we'll calibrate it. And we're providing 4-week calibration promises on these. And this is pretty cool, because right now the workflow for many people is to send their glider back to the manufacturer, have the manufacturer take out the GPCTD, have the GPCD sent to their manufacturer, have that calibrated, and then have it sent back to the glider manufacturer and sent back to you. For people in North America, that's a little bit quicker, but for people the rest of the world, it can take a very long time. And sometimes your gliders are out of commission or out of operation for months at a time. With this user removable wet bay system, you can take it out, send it directly to us, we'll calibrate and send it back. And if you had a second Legato CTD, you could actually do a hot swap in the field, plug this one back, plug in the correctly calibrated one, and be ready to go with essentially no downtime. The other opportunities is the silent operation. So there's no pump, which means it's totally quiet. It will improve passive acoustic studies, but also may improve your measurements of turbulence. If you've got a Rockland Scientific turbulence probe on it, there's no vibration from a pump, so it just totally removes that frequency of noise, of motion from the measurement itself. And as I mentioned, it functions as a sensor hub. So what that means is that you can easily work with us to integrate new sensors, such as maybe oxygen sensors, turbidity, PAR, fluorescence, things like that. We manage all of the sampling and power within the Legato, and you get that into your glider as one data stream. That means it's not complicated to add new sensors. Let me show you what that looks like a little bit. Here in this glider, you can see the Legato CTD. This is in a wet bay, so this area is flooded. There's one connector out the back, as you can see here, and that plugs into the glider. So you just have one connection point to the glider. But then we put other MCBH connectors on the Legato itself, and we can position these in a variety of places on the Legato. They can come off the front, they can come off the bottom in different positions, and we give you some of that choice. And then you plug your other sensors into that. So for example, this has 2 connectors on it. You can plug in RBR CODA TODO oxygen sensor and perhaps an EcoPuck in here. And let me show you how that actually works in practice. This is a Legato CTD integrated into the Teledyne Slocum glider. This is the G3, which has a new option for a wet bay that Teledyne's releasing. You can see the Legato here on the front with ports on both the port and starboard side for other sensors, as you're familiar with. And this is it in real life. Here you can see the Legato on the top. And if you see a little bit on the side here, there's an eco-puck. And on the side here is an RBRlegato TODO optical sensor. And both of these are connected with interface cables to the Legato. And Legato has one connection into the glider. Here you can see integrated on the standard G2 dry bay. So this is in the same place that the GP CTD sits, typically under the wing. And this is what it looks like in a dry bay configuration. We're also working with a variety of other glider platforms. Here you can see the Sea glider, which is now supplied by Hydroid and HHI. This is a dry bay, this is a wet bay system, which goes in the back in the hatch. And this is a really nice implementation that Hydroid has created to put the GPCTD next to the Legato on the same glider in the same bay for some comparison studies. This angle actually gives you a really nice view. You can see the really wide opening and short path length for the water to flow through. So you can see how it has really nice natural flushing through this wide bore. But we're also putting the Legato on a lot of other small AUVs. It's really pretty exciting. Here we're on the BAE Riptide AUV. Here we're on the Teledyne Gavia AUV. And more recently, we've been integrated into the Artesis NemoSense small micro AUV. And now you can see this great photo from Applied Physics Lab at the University of Washington. This is Luke Rainville and Jeff Schilling from APL UW, how they've deployed it on their sea gliders that they operate. They've got a hydrophone behind here and the Legato CTD right here. We're going to be sharing a little bit more data from their measurements shortly. You can see Alcimar has been busy integrating the Legato on their Sea Explorer glider. They have two different flavors. This is, you could consider it a backpack style Legato or an external Legato. Here it connects with an MCBH connector directly in a vertical aspect down through one of their ports. And they put on this fairing to help improve flow around Legato. They're shipping these for customers that use hydrophones in the nose cone, where there's not room in the nose cone to put a CTD because of the hydrophone, and they want the quiet performance. So here you can see it in real life being deployed. But they've also developed a new section, which is the more classic integration in the nose cone itself. Again, this is a flooded area. This is the wet bay Legato CTD in the nose cone. And you can see they have other sensors which can plug directly into the Legato. And then the Legato has one single connection into the Sea Explorer glider. So to improve performance and to make sure you get really nice performance without a pump, we wanted to make sure that we were going to have good natural flow. Natural flushing, which will improve measurements, improve response time, and reduce salinity spiking. So we created a little CFD model to look at flow around and through the Legato. And what the model indicates and what we've shown in real life is that we have really nice natural flushing. The background flow shown in about yellow speed propagates right through the glider and comes out. It's a low drag system. There's nothing really to snag or catch anything, and you've got nice natural flow. But then we wanted to actually do some real experiments in some laboratory facilities before we released this. So we 3D printed a mini glider form. This hull section in red, orange, and blue was 3D printed over probably many days, maybe even many weeks of 3D printing. And we took it to Ray Schmidt's double diffusive tank at Hui. And for those of you that are unfamiliar with this, it's a little bit more than 1 meter wide and several meters deep. And they can put cold, fresh water near the surface and warmer, saltier water at depth. And they can create a really sharp gradient. In this case, the gradient was at about 3 meters depth. And then we can plunge this glider hull with CTD through that interface, and we can make some measurements. What we've done, and it's a little hard to see here, but we've taped on the left at the same location as the Legato itself, an RBR Duet TD sensor with very fast sampling rate. So this is measuring the water at the same location as Legato, but sampling it really fast, I think at 32 Hertz, and with very quick response time. So we're using that as the reference measurement. And in this case, you can see the black line is the reference temperature. And you can see this really strong gradient going from about ambient temperature, 23 degrees, to about 30 degrees at around 3 meters. And then we measured the Legato temperature, which is this blue line, and Legato salinity or conductivity converted into salinity, which is the red line. And so the blue line you would expect to have some time lag just because of the response time for the sensors. And for the salinity, you expect to be pretty close, but with a little bit of a salinity spike because of the unaligned temperature. And then when we make the corrections using some of the tools from Lewick and Piccolo and Morrison, you can see that the blue temperature gets corrected quite closely, and the orange salinity, the dashed line, gets corrected quite closely with no salinity spiking. We also wanted to look at the natural flow through the conductivity cell as a function of flow rate, because we know it's not pumped. We know that vehicles will be traveling through the water at many different speeds, and we wanted to see how that worked. So here we have conductivity as a function of depth, and these scales are a little bit different. So you have to see, again, the main thermocline is around 3 meters here. And what we did was deploy the Legato. We plunged this whole glider through the interface at different descent rates, at different speeds going down to simulate different speeds through the water. We deployed it from as slow as about 10 centimeters per second to as fast as about 1 meter per second. And what you can see is that the change in conductivity is about the same at all flow speeds. So there's no real dependence between forcing water through the conductivity cell, the time response, and the flow speed. There are a couple wiggles in here, which we're attributing just to some general mixing going on at that gradient as we continue to plunge it and bring it back. We did let it rest, but it didn't become complete equilibrium and gradients and that sharp gradient again. There became a little bit of mixing during those multiple tests. Now we can look at some data from some of our customers in the field. This again is from Luke and Jeff at APL of University of Washington. Back in September, I think late September, they deployed one of their sea gliders with Legato offshore of Guam, and they took lots of measurements. It ran through October, November, I think even some of December. It did about 400 dives to 1,000 meters. They've collected the glider since then, of course, and all of these data are available on their website. You can go to their website linked here. This was on Sea Glider 178. But here you can see some really nice profiles down to 1,000 meters of salinity in blue and of temperature in magenta and red. You can see the temperature ranging from 30 degrees near the surface, pretty sharp temperature gradient at about 100 meters, going down to what we'd expect, which is about 4 or 5 degrees in the deep water. The Legato CTD has also been deployed on some other gliders, this one in some polar regions of the Arctic. And here you can see very cold temperatures below the thermocline, fairly warm at the surface. And this one also had an oxygen sensor on it, an RBR CODA TODO oxygen sensor. And here you can see the very low oxygen measured below about 200 meters and quite high oxygen measured in the surface mixed area. And this was deployed again to 1,000 meters over the course of many weeks before it was recovered. So let's talk a little bit about dynamic errors and corrections for gliders and what we've tried to do to help you get the best data quality going. So anytime people are profiling through a strong temperature gradient, you can introduce some dynamic errors in temperature and conductivity because it takes some time for the sensors to adjust to the changing environment. So the 3 things you have to address would be that it takes a finite time for the heat to transfer out of the thermistor. It takes amount of time for the water actually to pass through the sensors, to pass over and through the sensors. And of course, the sensors, the temperature sensor and the conductivity cell are not exactly co-located in space. So you need to make a little bit of corrections to adjust for that small difference. It's important to note that dynamic errors affect all CTDs, electrode-based CTDs, inductive CTDs, and there's been a lot of work published in the community for decades on this. It's not something new. We're just trying to help you understand how to improve it. Dynamic errors are magnified in derived variables such as salinity and density. You'll see salinity spikes, and you'll see density instabilities where there looks like there's lower density water below higher density water. Actually, I think it was 2 weeks ago, RBR gave a really nice webinar on CTD dynamic performance and corrections through gradients. You can go to our webinar page, you can read that presentation, you can watch the video, and you can learn a lot about it. What we're going to do here in just a couple slides is address the high-level recommendations for use on the gliders. So there are 3 primary causes of dynamic errors in CTDs. This page will show the first 2, and then the next couple pages will show the third one. The first is that there's the temperature sensor has a time constant, and that's how much time it takes for the heat to diffuse through the thermistor. As I mentioned, the Legato has typically the standard thermistor, which has about a 1 second time constant. It's actually a little bit faster than that, but we just say it's 1 second. And then we can provide the Legato with a fast thermistor, which has about 0.1 second time constant. That's what we call the fast. So certainly whichever thermistor you have, that will affect how long it takes for the heat to diffuse through the thermistor. The second aspect is about aligning conductivity and temperature together so that you lag one of them or advance the other one so that you get them aligned in time and space. And so there's a small spatial difference, spatial separation between when water flows over the thermistor and when it flows into the core of the conductivity cell. The physical spacing is 36 millimeters. And so depending upon your speed through the water, this is not vertical descent, this is speed through the water. It will take a small period of time for the water parcel to touch the thermistor and then move into the conductivity cell. An order of magnitude estimate is that if you're moving at 36 centimeters per second, then it will take 1/10 of a second for the water to pass through the thermistor, into the conductivity cell. If you're moving a little bit slower, it'll take a little bit more than 0.1 seconds. And now what we've done is calculated some optimal lags that you can use when you're doing your CT lag correction in post-processing. If you have the flow rate or the speed of the glider through the water, if you have that as an output from your glider data or from your model or from your glide angle, and if that's time varying, then we give you an equation where you can create a time varying lag. Or if you want to just approximate it with the common speed through the water, which is around 20 to 40 centimeters per second, then you can use an approximate lag of 0.94 seconds. And most of this lag is due to the thermistor time constant, which is a little bit faster than 1 second. And a small portion of this lag is due to the physical spacing offset. And here you can see what even that small change in aligning the time by 1 second or even less can do. Here we see a profile of temperature down to 600 meters. Again, these are data collected by Luke and Jeff at APL, University of Washington. This is Guam, and this is their deployment off Guam. They ran most profiles a little bit north of Guam. And we have the black lines, which you can see a little bit below the red lines. This is the downcast and upcast uncorrected. And then we have the advanced or the lagged time by just about 1 second. And in this case, they fall right on top of each other because over 600 meters, you can't really see that we're shifting the time by less than 1 second. Here's the raw conductivity measurement. There's no corrections or lags made there. And then we can see salinity. And as we know, salinity is a derived variable from conductivity and temperature. And the black is the uncorrected, and you can see a lot of spikes. The spikes are in areas where the temperature is changing most rapidly. There aren't any really strong gradients here, but even with these small temperature gradients, you can get some spikes in salinity. It's probably important to note that this is actually just a small salinity range from 34.2 to 35.2. So we're not looking at huge changes in salinity, which makes the spikes stand out a little bit more. But you can still see there are some spikes. But when we align the temperature and conductivity better in time by shifting it just a little bit less than a second, we can see we eliminate almost all of those spikes. So it's a very simple post-processing step you can do to greatly improve your glider data. Okay, the third thing that causes dynamic errors in CTD is the concept of thermal mass. And it's really how the exchange of heat between the conductivity cell and the water changes the conductivity measurement. And so thermal mass tends to generate, again, artificial density inversions at sharp gradients. Here we can see a profile. This is actually Argo float data going through a staircase of density changes. And here the black line is uncorrected. And when we're not correcting for thermal mass, we can see that, that we get this lower density step just before a big change. And this is a density inversion where we have density that looks too low compared to the density above it and would be unstable. And then we can run the corrections, which is some based on work from Lewick and Piccolo and Morrison, 1994. This is stuff that I'm not an expert in, but most people that are doing the work know. These are tau and alpha variables that are used in the correction process. And when we run through that, we can see we remove these density instabilities and actually get really nice red profiles of correct density measurements. And the work that we've done for the Legato show that some recommended thermal mass corrections would be a tau of 11 seconds. And when you put tau into the variable for alpha, you get a number of about 0.83. Sorry, 0.083. Okay, so moving on to the sensor hub concept. As I said, the Legato can integrate all of the sensors that normal RBR CTDs integrate. So these would be commonly temperature sensors. If you wanted to have an external temperature sensor to measure atmospheric temperature, I'll show you about that in a second. Of course, optical dissolved oxygen, the CODA TODO or the underoptode are two common oxygen sensors that we integrate. Fluorescence, if you want to measure chlorophyll, turbidity. We even integrate the eco-puck commonly, as well as PAR sensors. Moving very briefly into the CODA TODO, this is a really nice optical dissolved oxygen sensor. We use the same foils actually that Andra uses, so we're going to get about the same accuracy and stability as a standard underoptode. It has an extremely high temperature accuracy measurement of 0.002 degrees C. But most interestingly is that, again, the power consumption is really low. It's only about 20% of the underoptode. It's a little bit skinnier than the optode, which means it's a really nice fit for gliders in terms of the form factor, the response time, and the power requirements. It's rated up to 6,000 meters, so it will carry your gliders anywhere that you want to use them. Another kind of cool application is how glider are starting to measure atmospheric temperature when the tails are in the air for data telemetry and positioning. This atmospheric measurement gives you a really nice variable to provide for the climate modelers that are looking at air-sea interactions or weather modeling to have a nice sea surface atmospheric temperature measurement. The TODO, the optical oxygen sensor, could also be mounted in this same location where you get nice measurement of temperature from the TODO aspect of it, but also a measurement of oxygen in the air, which would be 100% saturation to help you constrain any type of long-term drift of the oxygen over longer glider deployments. So we're just about concluding. I think in general, we're really excited about the opportunities that the glider CTD is providing to folks. Of course, it's going on more platforms, which is pretty exciting. It's helping people collect better data, helping people get longer missions, integrate more sensors, and hopefully create more collaborations with each other and with RBR. So, so that's a summary for the Legato. Before we take any questions, I want to quickly tell you about what's coming up next for our webinars. The next one, next week, same time, same place, Greg Johnson will be speaking about RSK tools. This is a free MATLAB toolbox for post-processing, including some of the corrections we spoke about today. After that, Greg's actually got a second one the following week, and we're going to open up our CTD calibration lab for everyone. We're going to take you in there and tell you all about what we're doing for our high accuracy CTD and other sensors that we're calibrating. And finally, the last one in the lineup at the moment will be me again, for better or for worse, speaking about wave measurements for ocean, coastal, and transient wave studies. And I'll actually be joined by Kurt Sterlazzi from the USGS Santa Cruz office to look at how they've been using the RBR wave loggers for their own coastal wave measurements. So with that, I'm going to say thank you for joining. I could see there was some interesting chatter on the chat group, although I haven't been reading it because I'm not that good at multitasking. But what I'm going to do is invite Greg, if he's available, to jump in on video and try to summarize what some of the questions are and open the floor to new questions. So thank you for joining here.